A common approach to converting continuous transfer functions to their discrete equivalents is the backward difference approximation. We can see where this comes from if we start with something like, and we can approximate this sum term by our standard Riemann sum, and we can then convert this to the Z domain using the techniques that we are familiar with. Remember that we are working in deviation variables, so we can write that on the other side in order to get Pz. And we end up with an expression like this. Now, this sum term can be expressed, if we think about that as an infinite sum, or in other words for large n, that simplifies to 1 over 1 minus z minus 1. And we are left with a discrete transfer function with only a finite number of terms. And if we think about what that looks like, remember that in the Laplace domain, a PI controller, or let's say the integral part of a I controller, would look like this. And in other words, if we kind of compare terms here, to make this easy, I'm going to write this as and something similar over here. So if we compare these terms, the parts that are in common over here, it would appear as though we can make this kind of substitution, which says that S is approximately equal to 1 over 1 minus Z minus 1 over delta T. Now, an important thing to notice, this idea is very useful because it allows us to take an arbitrary transfer function, which perhaps was this transfer function over here. We do the substitution and we arrive at a discrete transfer function. However, it is important to understand that this is an approximation. And so therefore, like most approximations, it's simpler, it simplifies our calculations, but it is not more correct. The correct expressions for transfer functions we'll cover in a following lecture, but it's important to understand that this approximation is not 100% correct, and it's a useful exercise to the reader to take some of the elements in the table using the backward difference approximation and what is in the table, and to see how step size, for instance, affects that approximation.